Greetings, dear students. Today we'll be looking at elastic properties of solids. A body is said to be elastic if it regains its original shape and size after undergoing a stretch or compression. Now let's talk about Hooke's law. Hooke's law states that provided the elastic limit is not exceeded, the extension E in an elastic material is proportional to the load or applied force F. Mathematically, F is equal to KE, where K is the force constant of the material. Example, spring or wire, also known as stiffness or elastic constant in Newton per meter. Let's solve an example under Hooke's law. So let us consider this example. A spring has a natural length of 12 cm when stretched with a force of 10 Newton. It extends to a length of 17 cm. A. Determine the force constant of the spring. B. Calculate the force required if the same spring is to be extended by 8.0 cm. C. What assumption have you made in these calculations? Solution. The extension of the spring E will be equal to 17 cm minus 12 cm, which will give you 5 cm. When you convert to meter by dividing it by 100, you will now have 0.05 meters. Using Hooke's law, which says that F is equal to force constant times extension. From the question, the force is 10 Newton and the extension is 0.05 meters. We are to look for K, which is the force constant. When you divide 10 Newton by 0.05 meters, you will have K to be equal to 200 Newton per meter. In the B part of the question, since the same spring is used, the force constant K still remains 200 Newton per meter. Applying Hooke's law once more, that force is equal to force constant multiplied by extension. F will be equal to 200 Newton per meter multiplied by the new extension, which is 0.08 meters. And when you do that, you will have force to be equal to 16 Newton. The C part of the question, we have assumed that the limit of proportionality of the spring was not exceeded in both cases. Otherwise, Hooke's law cannot be applied. Example 2. An elastic wire extends by 1.0 cm when a load of 20 grams hangs from it. What additional load will be required to cause a further extension of 2.0 cm? Solution. The force exerted by a mass of 20 grams while we're having acceleration due to gravity to be equal to 10 meters per second squared. So to convert the 20 grams to Newton, we'll multiply the 20 grams by 10 and divide by 1000. The division by 1000 is to convert it to kilogram, while the multiplication by 10 is to convert it to force in Newton. By Hooke's law, again, we say that force is equal to force constant K multiplied by extension E. Now we'll have our force to be equal to 0.2 Newton, and we're looking for the force constant. So we'll convert the 1 cm to 0.2 meter by dividing it by 100. When we do that and use the value of extension to divide the force, we'll have the force constant K to be equal to 20 Newton per meter. Now, the other part of the question, let M in kg be the additional load required to extend the wire by a further 2 cm, which when you convert to meter will be 0.02 meters. The total extension is now 3 cm or 0.03 meters. That is when you add the previous 1 cm extension to this 2 cm. Force exerted by the new load is 0.02 plus M multiplied by 10 will be equal to the force constant times the new extension. Take note that the 0.02 is the previous 20 grams. When you divide it by 1000 to convert it to kilogram, you will have it to be 0.02 plus M to be the additional load. Now the 10 is the value of acceleration due to gravity. So when you multiply the bracket by 10, you have 10 M plus 0.2. Now put the value of the force constant being 20 and multiply it by 0.03. When we do that, we'll have 10m plus 0.2 to be equal to 0.6. When you solve out by moving 0.2 to subtract from 0.6, you have 0.4. Then 0.4 divided by 10 so that you can calculate m will give you 0.04 kg. When you multiply 0.04 kg by 1000 to convert it back to grams, you will have m to be equal to 40 grams. Now let's look at Young's modulus. Young's modulus is defined as the ratio of tensile stress to tensile strain. Young's modulus is equal to stress divided by strain. Tensile stress is the ratio of the force acting on a material to the cross-sectional area of the material. Stress is equal to force divided by area. Unit of stress is Newton per meter squared. Tensile strain is the ratio of the extension of a material to its original length. Strain is equal to extension divided by original length. It has no unit. The SI unit of Young's modulus is Newton per meter squared. The larger the value of the Young's modulus of a particular material, the stiffer or less elastic the material. Example 3. A force of 40 Newton applied at the end of a wire of length 4 meters and diameter 2.00 millimeters process an extension of 0.24 millimeters. Calculate the A. Stress on the wire, B. Strain in the wire, C. Young's modulus for the material of the wire. Take pi to be equal to 3.14. Solution. Stress is equal to force divided by area, which is equal to F divided by pi r squared. Here we're using pi r squared because the wire's cross-sectional area is circular. Radius r is equal to diameter divided by 2. Now when the diameter is 2 millimeters, radius will be equal to 2 millimeters divided by 2, which will give 1 millimeter. When divided by 1000 to convert it to meter, you have 0.001 meter. Now, F is equal to 40 Newton and R is equal to 0.001 meter. And remember that pi is equal to 3.14. Now, when we substitute the values, stress is going to be equal to 40 divided by 3.14 multiplied by 0.001 meter squared. When we solve out, we're going to have our answer to be equal to 12.74 times 10 raised to power 6 Newton per meter squared. Strain is equal to extension divided by original length. In symbols is equal to E over L. Where L is 4 meters, extension is 0.24 millimeters. When converted to meter by dividing it by 1000, we'll have 2.4 times 10 raised to power minus 4 meter. Strain is now equal to 2.4 times 10 raised to power minus 4 divided by 4, which will result to 6.0 times 10 raised to power minus 5. Remember that strain has no units. Now, having calculated stress and strain, we can now calculate Young's modulus using stress divided by strain. We substitute the value of stress being 12.74 times 10 raised to power 6 divided by 6.0 times 10 raised to power minus 5. And when we do that, we'll have our final answer to be 2.12 times 10 raised to power 11 Newton per meter squared. Thank you very much. See you in our next class. God bless you.